We're going to start our new chapter on thermochemistry, which is just pretty much the study of heat and chemical and physical changes. The first law of thermodynamics, which is often called the law of conservation of energy, simply means that energy can be converted from one form to another but cannot be created or destroyed. Basically, the energy of the universe is constant, is what we're saying. So you can turn electrical energy into heat. You can turn chemical energy into heat or into electricity. There's all kinds of energy transfers and conversions, but that energy is constant. The energy in the universe remains constant throughout all of these conversions. So as we start our study of energy, we're actually going to create a chemical fuel that we're going to turn and use the energy and convert that stored potential energy into chemical energy and a release of heat. Here are two examples of turning one type of energy, wind energy, into electricity, and then you've got your hydroelectric power as well. So the two basic types of energy are potential. This is energy due to the position or composition, and it can be converted into work or heat. And then you have kinetic energy, which is due to the motion of the particles. Kinetic energy has an equation which is 1/2 mv squared. So m is equal to the mass of the particle and v is the velocity of that particle, and you can see that there's a square effect on that. So kinetic energy, which is heat, which is the basic energy we'll be dealing with in this chapter, is due to the motion of particles, and that potential energy is due to the position. And in chemistry, that's pretty much the bonding and the position of that bond. Kinetic energy is several different types of motion. You have translational motion, which is the movement of one particle from one area to another. So when you have gas particles moving from one position to another, that's your translational motion. And then within the molecule, you have vibrational motion, which means these bonds can stretch and vibrate, and rotational motion, which means the whole molecule can rotate. And the more bonds you have, the more of that rotational and vibrational motion that you can get. Energy is defined as the ability to do work or transfer heat. And heat itself is defined and get this thing to work. There we go. Heat is the form of energy that flows between two objects because of a difference in their temperature. So in order for heat to transfer, objects must come in contact with each other and they must have a difference in temperature. Okay? So energy is the ability, okay, to do work or transfer heat. Remember, there are two forms of that energy, potential and kinetic. Heat itself is the form of energy, the kinetic energy, that flows between two objects when they have a difference in temperature. Heat cannot flow between two objects with similar temperatures. So heat is that transfer of energy, and you simply need to be able to follow that direction of heat flow. Here, the heat is flowing from the burner into the kettle. Here, heat is flowing from the girl into the surrounding ice. So heat either flows in or out. If heat is flowing out this way, okay, then the ice itself is taking heat in while the hand is losing that heat. Here, the kettle is taking the heat in while the surroundings are losing that heat. It's always a trade-off between energy transferred in and energy transferred out. Temperature is a measure of the average kinetic energy of the particles in a substance. It is the measurement of the motion of those particles. So temperature and heat are not the same. Temperature is a kinetic energy, and again, its formula, this out of the way, is 1/2 mv squared. It's the motion of the particles. So when you place your thermometer in the surroundings where heat is absorbed, the glass of the thermometer absorbs the heat energy, causes the motion of the molecules of the glass to speed up. They transfer their energy to the mercury or the alcohol, and those particles speed up and the temperature rises. So temperature itself is a measure of the average kinetic energy. In any sample, there are many kinetic energies. There is an average that the thermometer can read and is determined as temperature. Temperature does reflect only the random motion of particles, so it's related to the kinetic energy. Heat involves a transfer of this energy between two objects due to a temperature difference. So if you have two objects at a different temperature and you bring them into contact where that thermal energy can be transferred, the energy will transfer from the higher kinetic energy to the lower, and this transfer will go back and forth until they reach the same temperature, which means the speed or motion of those particles would be equivalent. They would be at the same temperature.
Molecules in the gas phase are in constant motion with a kinetic energy proportional to the system temperature. In this example, gaseous molecules at two different temperatures are separated by a thermally conductive barrier. The greater kinetic energy of molecules on the left is transferred through collisions with the wall to the molecules colliding with the right-hand side of the wall. The result is a decrease in kinetic energy and temperature on the left, and an increase in the kinetic energy on the right. Eventually, the two containers reach a thermal equilibrium, where the kinetic energy and temperature on both sides are constant.
So, as you noticed in this, the higher temperature had the faster moving particles. As they hit that thermal barrier and transferred that energy, and that heat, that kinetic energy, to the cold, then those molecules would speed up until they reach that thermal equilibrium with the equal temperature, meaning equal motion of molecules. The direction of heat flow is pretty straightforward. If you take this water at 20.7 degrees Celsius and you heat this metal up, you know that the temperature of this metal is going to be higher than the temperature of the water. When you place the metal into the water, the heat will flow from the higher kinetic energy, from the higher energy to the lower, until the metal and the water have reached a thermal equilibrium, where the temperature remains constant. So placing it in will give you an increase in temperature. We don't know if it's reached thermal equilibrium until there is no longer a change in that temperature. The kinetic energy from the hot metal is transferred to the colder water until there is a constant temperature. Direction of heat needs to be given with a sign. The sign for direction of heat is given as a positive or a negative value. Negative means heat leaves the system. Positive means heat enters the system. Exothermic, heat is exiting or leaving the system. Endothermic, with a positive delta H, means heat is entering. Delta H means the change in heat. So up here, the metal right here is taking in heat. So if you're referring to the metal, that's a positive delta H change. When the metal is transferred into the water undergoes an endothermic reaction as it absorbs heat while the metal undergoes an exothermic reaction. These are not negative and positive numbers, they are directional signs referring to the direction of heat flow. The system, okay, and the surroundings, so the system here would be the match. The surroundings would be everything else. When you light that match, heat flows out. That would be exothermic. That would give you this negative delta H. To melt ice requires that the ice absorb heat energy. So energy would be entering the system from the surroundings. That would give you an endothermic or a positive delta H value. Exothermic reactions release heat. They release heat to the surroundings, which means the products have lower energy than the reactants. Exothermic reactions with a negative delta H release heat into the surroundings, so the potential energy of the reactants is lower than the products because that potential energy has been converted into the kinetic energy of heat, lowering the potential energy of the reactants in forming the products. So the products have lower potential energy. For an endothermic reaction, the opposite is true. The reactants absorb energy, and the products now have more potential energy than the reactants. So heat was absorbed into the reaction to create higher potential energy products, giving you a positive delta H sign. A full potential energy diagram also includes this little energy barrier called the energy of activation. So all reactions need some energy of activation to get going, but overall you have reactants over here and products. So you have lowered your energy left in the form of heat usually. That gives you that negative delta H, or an exothermic reaction. For an endothermic reaction, you still have this energy barrier that you need to get over. You still need that activation energy. Heat enters in order for the reactants to climb that energy barrier and become products. So the products have more energy than the reactants. That is your positive delta H and reflects an endothermic reaction. So every energy measurement has three parts: a unit, we'll usually use joules, but calories can be used, a number, a value, a magnitude, and a sign to tell you the direction of that energy flow. Remember, those positive and negatives are not positive and negative values. They are directional indicators. They tell you whether it is exothermic or endothermic. So let's look at this simple reaction, see if we can go through the thinking in terms of energy. You actually could have two processes occurring here. You need to be told which one you're looking at. So we're either taking this liquid water and freezing it, or we're taking the solid water and melting it. So we're going to go with the melting. In order for the solid structure of ice to turn into the more disordered liquid structure, you must add heat energy to break those intermolecular forces and turn the solid into a liquid. Anytime you're doing a physical change where a solid becomes a liquid, you are adding heat energy to change the potential energy of those substances. So melting requires heat energy. That is an endothermic process. So when you put ice into your water, the cold does not jump out of the water, jump out of the ice and get in the water to make the water cold. In fact, the ice absorbs the heat. It's an endothermic process of the ice going from its solid to its liquid state. So it is absorbing that heat, which is an endothermic process, which means that heat is leaving the water going into the ice in order to go through this process, and the temperature of the water will drop. The temperature of the water will drop to the temperature of the ice as long as there is ice in there, and that will give you an equilibrium temperature of 0 degrees Celsius. If water freezes, in order to freeze, you have to take the liquid state and turn it back to the solid state. The solid state has lower potential energy, so you need to lose energy. So if you're losing energy, you have to be giving off that energy. So you've got an exothermic reaction. Your liquid is losing its heat, okay, in order to form the more ordered solid state. So freezing is actually an exothermic process. Boiling, in order to boil, you must take heat energy into the liquid water to go from the liquid to the gas state. That would be an endothermic process. When water vapor condenses on a cool system, so to condense, you're going from a gas to a liquid. The gas has higher potential energy than the liquid. In order for the gas to condense, it needs to lose energy. It needs to give off energy so that it can form these liquid droplets. So that has to be an exothermic process. In order for a gas to turn into a liquid, you must release that heat energy. So condensation is an exothermic process. Evaporation is an endothermic process. What you see here is a little confusing because this up here is actually condensed water, where you had water leaving the liquid state, going into the gas state, and then as it hits the cooler air, it condenses back into the liquid state. Otherwise, we would not be able to see it. Whenever you can see water vapor, it's in the condensed state. You're seeing the water droplets forming a liquid in the cool air around them. But the process of evaporation itself, to go from liquid to gas, which is higher potential energy, requires energy. That would be endothermic or a positive delta H. So again, this one is a little clearer, this diagram, without involving the condensation. In order for water that is bonded with hydrogen bonds to itself, we're not breaking these bonds. That would be a chemical reaction. We're just breaking the attraction of water molecules for each other. Okay? And when you do that, the higher energy molecules on the surface can break free and become the gas state. In order to break free, in order to break that attractive force, you must add heat energy. So it's an endothermic process to turn that liquid to the gas state. Again, ice melting would require energy, so we're back where we started. So make sure that you have a really good intuitive understanding of the direction of heat flow. Okay? In order to melt, you must absorb heat energy. If you're absorbing heat energy from the surroundings, that could be the air or the table or whatever surface, if you're absorbing that heat energy, then that is a positive or endothermic process. To help you get it straight until you can intuitively understand it, when you have the solid, and this is only for these physical changes, chemical changes are different, so only for physical changes of converting solid to liquid to gas, or gas back to liquid back to solid. The solid has the lowest potential energy. The atoms and molecules in a solid are close together. In a liquid, they are further apart, so you've had to add heat energy to break those attractive forces. And in a gas, they're even further apart, so you needed to add more heat energy. So in going from a solid to a liquid to a gas, that is always an endothermic process. Therefore, going from a gas to a liquid to a solid is always an exothermic process. So writing this little cheat sheet will sort of help you when you're trying to decide evaporation, condensation, boiling, freezing, and so on. Eventually, your understanding will be greater and you will not have to refer to this. But in the beginning, students find it helpful to write solid, liquid, gas, and then simply say, okay, if I'm going from a solid to a liquid to a gas, if I'm going up in potential energy, that's endothermic. If I'm going down, that's exothermic. For chemical reactions, okay, you can't use that. You have to look at whether or not the reaction releases or absorbs heat. Obviously, when you're burning, combustion, that's clearly exothermic in terms of the burner releasing that heat in the form of combustion of that gas. That gives you a negative delta H. So when you're looking at heat, you really have to get heat and temperature really clear in your head and the difference between them. Obviously, if it's the swimming pool versus the hot cup of coffee, we know that the hot cup of coffee is at a higher temperature, no doubt about it. You stick a thermometer in there, you're going to get the motion of the hot coffee molecules. They're moving much faster. Your temperature is greater. But in terms of possessing more heat energy, there's quite a bit of difference between them. The swimming pool, especially the enormous amount of water in that swimming pool, would definitely possess more heat energy. Heat is calculated. Heat is a mathematical calculation that uses the mass of the substance, the specific heat of the substance, and the temperature of the substance. So we can say that the hot cup of coffee obviously has a higher temperature, but there's much more water in the swimming pool. So when we do these calculations, and then of course we've got to understand what this C means, this specific heat capacity. Both of these, the coffee and the swimming pool, are mostly water, so that would be pretty consistent. But the large mass of water here would definitely give you more heat energy stored in that swimming pool. So when you calculate heat energy, you've got a 4-variable equation, and you'll be given 3 of the variables. The unit for heat is joules. The unit for mass is usually grams. Temperature is degrees Celsius. And specific heat capacity is joules per gram degree Celsius. This is the amount of heat that 1 gram of this substance can absorb before its temperature changes by 1 degree Celsius. And every single substance has a different specific heat capacity. It's determined by the bonding and the structure and the material that the substance is made out of. So it's the amount of heat energy that 1 gram of the substance can absorb before its temperature changes by 1 degree Celsius. So its unit is joules per gram degree Celsius, the amount of heat that 1 gram of a substance can absorb before its temperature changes by 1 degree Celsius. So even with water in the liquid state versus the solid state, liquid water can absorb 4.184 joules for every gram before it changes by 1 degree Celsius, but ice can only absorb 2.03 joules for every gram before its temperature changes. Metals typically have very low specific heat capacities. That's one of the properties of metals. They are good conductors of heat and electricity. It only takes for aluminum 0.89 joules before a gram of it changes its temperature by 1 degree, and iron takes even less, 0.45 joules, before 1 gram changes its temperature by 1 degree Celsius. So specific heat capacity and calculation of heat will be what we will focus on in our next podcast. The high specific heat capacity of water gives it its ability to absorb tremendous amount of heat energy before its temperature changes, which is why we use it as a coolant in our car radiators. The connection between joules and calories, and occasionally we'll calculate in calories, is that 1 calorie is equivalent to 4.184 joules.